Okay, let's dive in. What if I told you that the most basic building blocks of arithmetic prime numbers, what if they have this secret life-shaping geometry?
Sounds pretty wild, yeah.
It really does. Prepare to have your whole idea of numbers and space stretched.
It is a fascinating collision, isn't it? Two worlds you wouldn't immediately connect. We're going to see how these primes, these kind of elusive numbers, they can actually act as architects.
Yeah, architects for some really bizarre but also beautiful mathematical structure.
Exactly.
And so our mission for this deep dive is really to unpack how prime numbers, just primes, only divisible by one and themselves, how they can be used to build these incredibly strange mathematical objects. On the simple number line, the unit interval from 0 to 1.
Like primes going rogue, you said.
Yeah, building their own little realities on the number line.
And along the way, you're going to meet three main characters, so to speak, each with its own, well, mathematical personality.
That's right. First up, we've got the Dynamic Prime Cantor Set, DPCS for short. Imagine a fractal, but instead of a fixed rule, it changes. It evolves based on the prime numbers themselves.
Then there's its more substantial cousin.
The Fat Dynamic Prime Cantor Set, or F-DPCS.
Right.
And finally, the really intriguing prime ghost line, the PGL.
And each one has these just mind-bending properties.
Totally. Like the DPCS, it ends up with 0 length, like nothing there lengthwise. But somehow it manages to have a full dimension 1.
Which is just weird.
So weird. Then the FDPCS, the name gives it away. It's fat. It keeps some size, some positive length.
It holds on to some measure, yeah.
And the prime ghost line, it's just full of holes, these tiny little prime-related holes. But in a really strange way, it still feels whole. Now, look, if this sounds a bit out there, trust us, we get it.
They can seem pretty abstract at first blush.
Definitely. But that's why we're doing this. We're going to pull out the core ideas, make them hopefully digestible, fascinating nuggets for you.
Think of it as maybe a shortcut to understanding some pretty cutting-edge math ideas.
Exactly, without needing the PhD first. So ready to explore this prime geometric landscape.
Absolutely. Let's kick off with the first one, the Dynamic Prime Cantor Set.
Okay, the DPCS. Now, many people have probably heard of the classic Cantor set, right?
Yeah.
That fractal dust you get by repeatedly chopping out the middle third.
The standard construction?
The DPCS is like that, but with a prime twist. The removal, it isn't fixed. It changes every step.
And it's dictated purely by the sequence of prime numbers, 2, 3, 5, 7, and so on.
What's really cool here is how that prime sequence gives you the blueprint.
Yeah.
So at each step, let's call it step K, we look at the K-teeth prime number, PK.
And for every little interval that's still left over from the step before, you divide it into PK plus 1 equals smaller subintervals.
Okay, so step 1, K equals 1. The first prime, P1, is 2.
Right.
So we take our starting interval, 0, 1, and divide it into 2 plus 1 equals 3 equal parts.
Standard first step, yeah.
Now, here's the prime part. We need to know how many primes are less than or equal to our current prime, PK.
That's the prime counting function, PK.
Okay, pi PK. It just tells you how many primes up to and including PK.
Exactly. So at step K, after you've divided into PK plus 1 pieces, you look at the index of each piece. Number them 1, 2, 3, up to PK plus 1.
Okay.
If that index number, let's call it J, happens to be a prime number and it's less than or equal to your current prime PK.
Then what?
Then you remove the open version of that subinterval. Just take it out.
Okay, let's walk through the first couple steps, make it really clear. Step 0, we just have 0, 1, simple.
Nice and easy. Then step 1. First prime, P1, is 2. Divide into 2 plus 1 equals 3 intervals. Now, the prime's less than or equal to 2. That's just 2 itself.
So the subinterval with index 2 gets removed.
Yeah, we're left with 2 intervals, 0, 13, and 23, 1.
Okay, hold on. That's exactly the same as the first step of the regular Cantor set.
It is, but wait for step 2.
Ah, okay. This is where it diverges. Step 2, the second prime, P2, is 3.
Right. So now we take each of those 2 remaining intervals.
0, 13, and 23, 1.
And we divide each of them into 3 plus 1 equals 4 equal pieces.
Okay, 4 pieces each. So 0, 13 becomes 0, 0, 1, 12, 1, 12, 2, 12, 2, 12, 3, 12, and 3, 12, 4, 12.
Precisely. And that 1, 23, 1, that's 8, 12, 12, 12. It becomes 8, 12, 9, 12, 9, 12, 1012, 1012, 11, 12, 11, 12, 12, 12.
Got it. Now the primes less than or equal to 3.
That's 2 and 3.
So from each set of 4 little intervals, we remove the ones with index 2 and index 3, the open versions.
That's the rule.
So from the first bunch, we remove 1, 12, 2, 12, 2, 12, 3, 12. We're left with 0, 1, 12, and 3, 12, 4, 12.
Which simplifies to 14, 13.
Right. And from the second bunch, we remove 9, 12, 12, 11, 12, 11, 12. We're left with 812, 9, 12, along with 12, 12.
Or 23, 34, and 11, 12, 1.
Okay. So end of step 2, we have 4 little intervals left. And yet you can totally see how this is already different from the standard middle third removal.
Completely different path. And this just continues infinitely. Step K uses prime pk. Now, structurally, it does share some traits with the classic Cantor set.
Like what?
It's compact, it's all contained, no loose ends.
Okay.
It's totally disconnected, just a dust of points, essentially.
Right.
It's perfect, meaning every point has neighbors arbitrarily close.
Uh-huh.
And maybe surprisingly, it's still uncountable. More points than whole numbers, even after all that removing.
Wow. Okay, so topologically, they're similar spirits?
In many ways, yes, but the size is where things get really wild.
Let's talk measure, Lebesgue measure, like its total length on the number line.
Yeah, how much stuff is left. Okay. At each step k, remember, we divide into pk plus 1 parts.
And we remove pk of them, the prime index ones.
So the fraction of the length we keep at that step is pk plus 1 minus pk, all divided by pk plus 1.
Okay, the proportion that survives step k.
Exactly. And the total measure, the total length of the final DPCS set is what you get when you multiply all those fractions together for every single prime infinitely.
An infinite product from k1 to infinity of that fraction.
Right. Now, the thing is, for any prime pk, which is 2 or more, there's at least one prime less than or equal to it, namely itself.
So pi pk is at least 1.
Which means that fraction, pk plus 1, is always a little bit less than 1.
Always keeping slightly less than the whole length at each step.
And here's the key insight. When you multiply infinitely many numbers that are all just slightly less than 1, that product converges to 0.
0. So after all that, the total length of the DPCS is nothing.
Absolutely 0. It's like we've meticulously removed so much step by step using the primes that in terms of length, there's nothing substantial left. It vanishes.
Okay, 0 length. But you mentioned something about dimension earlier.
Yes. The really mind-blowing part. Hausdorff dimension.
Which is like a more sophisticated way to measure fractal size, how it fills space when you zoom in.
Exactly. For the standard Cantor set, it's a fraction, log 2, log 3, about 0.63.
Less than 1. Makes sense. It's got gaps.
But for the DPCS, you need some heavy machinery, number theory, the prime number theorem.
And the result is?
It's been proven rigorously.
Yeah.
The Hausdorff dimension of the DPCS is exactly 1.
1. Wait. 0 length, but dimension 1, like a line.
Precisely. Let that sink in. It has no length, occupies no interval on the number line, yet its fractal dimension is the same as a solid line segment.
How is that even possible?
It means it fills the space, in a fractal sense, incredibly densely. So densely that its dimension gets pushed all the way up to 1, even while its overall length is 0.
So the takeaway here is a set can be super thin in length, but super dense fractally.
That's it. It's completely counterintuitive, but that's what the math shows.
Wow, and does it get to 1 quickly?
Actually, no. The convergence is known to be quite slow, which hints at just how intricate and subtle the structure is that the primes are weaving here.
A 0 length object that's somehow space-filling dimensionally. Okay, my head hurts a bit.
It's a lot to take in.
So that's the DPCS, 0 length, full dimension, all thanks to these dynamic prime architects. Shall we meet the next character?
Let's do it. The Fat Dynamic Prime Cantor Set, F-DPCS.
If the DPCS was about disappearing length, this one's different.
Very different. It's about keeping length. The F-DPCS construction is much gentler.
And for how?
Instead of removing intervals based on pi pk, at each step k, still governed by the prime pk, the total length of the set is only reduced by a specific factor.
Okay, what factor?
It's reduced by a factor of 1 minus 1 over pk squared.
1 over pk squared. So 14 at the pt step, 19 at the pp3 step.
Yeah.
Those are really small fractions we're multiplying by. Or rather, we're keeping 1 minus that fraction.
Exactly. We're keeping almost all the length at each step, like snipping away only tiny bits. You could picture it as removing very small symmetric intervals from the middle of each piece that's left.
So because we're only removing these tiny fractions, 1 pk squared at each step,
the total amount removed, even over infinite steps, isn't enough to make the whole thing vanish.
doesn't go to 0.
Not at all. In fact, the Lebesgue measure, the total length of the F-DPCS, is given by the infinite product of these factors we keep. The product over all primes p of 1 p squared.
Okay, another infinite product. Does this one have a known value?
It does, and it's quite famous in mathematics. It connects to the Riemann zeta function.
Ah, yes. Zeta of 2.
Precisely. This infinite product equals 1 divided by the zeta function evaluated at 2. And zeta 2 is known to be pi squared divided by 6.
So the measure is 1 over pi squared 6, which is 6 divided by pi squared.
That's the one,
Like
which is approximately 0.6079.
Okay, so the key thing, that number is definitely not 0.
Not 0 at all. It's positive. The FDPCS has positive measure. It's a fat fractal. A substantial chunk of the original length survives.
Right, it keeps a definite size. Now, dimension. The DPCS had 0 length, but dimension 1. What about this one, with positive length?
This is actually more straightforward. There's a fundamental result in fractal geometry.
Yep.
If any set on the real line has a positive Lebesgue measure, if it has actual measurable length, then its Hausdorff dimension must be 1.
Ah, so because the FDPCS has measure 6 over pi squared, which is positive.
Its Hausdorff dimension is automatically 1.
Okay, so both the DPCS and the FDPCS end up with dimension 1.
They do.
But for totally different reasons. One gets there despite having 0 length through sheer fractal density,
While the other gets there simply because it retains a positive amount of length.
That's a really striking contrast.
Yeah.
It shows how much the specifics of the prime construction rule matter.
Absolutely. Changing the rule from removing pi pk intervals to just reducing length by 1 pk squared makes a world of difference to the measure, even if the dimension ends up the same.
It really does. And it makes you wonder, what if you mess with the FDPCS rule even more?
Like how?
What if you decide, I don't like the prime number 5, I'm just going to skip the removal step associated with 5. What happens if we exclude certain primes?
Ah, now you're getting into the prime ghost effect. This is really cool.
Prime ghosts. Sounds spooky.
It is. So imagine we pick a set of primes, let's call it S, that we want to exclude. We just ignore them.
Okay, S is our set of bad primes we're ignoring.
Then we define a new set, let's call it F prime sub S. It's built just like the FDPCS using the 1 and p squared reduction factor, but only for the primes P that are not in our excluded set S.
Right, so we skip the reduction steps for primes in S.
Exactly. Now what happens to the measure of the length of this new set MF?
Does it go up or down?
It turns out to be the measure of the original FDPCS, that's 6 was, divided by the product of 1 and q squared, but only for the primes q that we excluded, the ones in S.
Okay, wait. Let's unpack that. We're dividing by a product of numbers like 1 and q squared. Each of those is less than 1. So the product itself will be less than 1. Unless S is empty, then it's 1.
Right.
And dividing by a number less than 1 makes the result bigger.
Exactly. The measure MFS is greater than or equal to the original measure MFS. By deciding not to remove the bits associated with certain primes, we actually make the final set fatter.
Whoa. So the absence of a primes removal step, you feel it as an increase in size.
It's like that prime leaves a ghost. Its lack of action means more length stays behind.
And can we quantify that? If we exclude just one prime, say prime q,
Yeah.
how much bigger does the set get?
Yeah, we can calculate the increase. Let's call it delta m sub q. It turns out to be 6 divided by pi squared times q squared minus 1.
Okay, 6 q1. What does that tell us?
Look at the denominator, q squared minus 1. If q is a small prime like 2, then q1 is 3. If q is a bigger prime like 11, then q1 is 120.
So the denominator is much smaller for small primes.
Which means the increase in measure, delta mq, is much larger for small primes.
So excluding the prime 2 has a bigger impact than excluding the prime 3.
Much bigger. If you exclude q2, the increase is 6.372. If you exclude q3, the increase is 6 bec t equals 3 4 Cs. That's smaller.
So the smallest primes leave the biggest ghosts when they're excluded. Their absence makes the most difference to the final size.
That's a great way to put it.
But crucially, even if we exclude some primes, as long as we don't exclude all of them,
The resulting set F2 will still have a positive measure. It'll be even fatter than the original FDPCS.
and because it has positive measure,
Its Hausdorff dimension is still 1.
so the dimension is really robust. It stays at 1 even with these ghostly increases in measure.
It seems to be yes. As long as you're doing some infinite thinning process based on infinitely many primes, even if you skip some, the dimension stays put at 1 for these fat sets.
Fascinating. Okay.
Yeah.
DPCS, FDPCS, prime ghosts. What's our third character?
Our final act is the prime ghost line, the PGL. And this one, we're shifting gears quite fundamentally.
How? No more removing intervals.
Exactly. Forget removing intervals. Now we're just removing individual points.
Okay. Which points?
We define a specific set of points, let's call it R. It's the set of all numbers you can get by taking 1 divided by a prime number raised to any positive integer power.
So 1 over p to the power k, where p is prime and k is 1, 2, 3, etc.
That's it. So you get 12, 13, 15, 17.
Primes in the denominator.
Then also 1, 2, 1, 3, 2, 9, 12, 1, 3, and 25, prime powers in the denominator.
And 1, 2, and on 18, 1, 3, and on 27, and so on. All combinations of primes and positive integer powers.
Okay, it's an infinite set of points. Are they spread out or
Yeah.
bunched up? They definitely bunch up near 0, right? As P or K gets large, one pin gets very small. But importantly, it's a countable set.
Countable, meaning you can list them all out even though it's infinite, like you can count the rational number?
Precisely. It's a countable infinity of points. Now, what do we know about the Lebesgue measure, the length of any countable set of points?
Is it 0?
It is exactly 0. Think of it like dust. No matter how many specks of dust, they don't add up to cover any real length. So the measure of our set R is 0.
Okay, the set of points R has 0 length. So what's the prime ghost line, G?
G is simply the original unit interval 0, 1, but with all the points from the set R removed, we just pluck them out.
So we take the line from 0 to 1, and we poke out holes at 12, 13, 14, 15, 17, 18, 19, 19, and 11.
Yeah.
All those points in R.
Exactly. Now, what's the measure, the total length of G?
It started with length 1.
Yeah.
And we removed the set R, which has length 0. So 1 minus 0.
Which is what?
The prime ghost line G has full Lebesgue measure.
Yeah.
Still has length 1.
It does. Even though we've poked infinitely many holes in it, removing those specific points doesn't reduce the overall length at all.
Wow. That is really different from the Cantor sets, where removing intervals, even tiny ones infinitely often, could wipe out the length completely.
A huge difference. Removing intervals takes away substance. Removing countable points, it doesn't.
Okay, measure is 1. What about dimension? Hausdorff dimension.
First, the set R itself, the points we removed. Any countable set has Hausdorff dimension 0.
Dimension 0, like isolated points should have.
Right. Now, the prime ghost line G, the interval with R removed, we already know it has positive Lebesgue measure 1, in fact.
And positive measure means?
Dimension 1.
So the PGL-G has full measure 1 and full dimension 1, just like the original interval we started with.
Exactly. Geometrically, in terms of length and dimension, it's essentially indistinguishable from the original 0, 1, despite having this infinite countable set of prime-related points missing.
It's like the ghosts of the points themselves, but their removal leaves no geometric scar.
That's a nice way to think about it. It really highlights that tension, doesn't it? Each point, one pine, has its own unique arithmetic identity.
Yeah, 18 is different from 19.
But geometrically, especially as they cluster near 0, they get incredibly close. Yet analysis treats them as distinct points with 0 measure each. Removing them doesn't change the overall geometric picture in terms of measure or dimension.
So it's a line full of these specific prime power holes, but it's still fundamentally a line segment in its size and how it fills space.
Pretty much, yeah.
Okay, let's try and wrap this up then. We've seen 3 really different ways primes sculpt things on the unit interval.
We have.
First, the Dynamic Prime Cantor Set, DPCS. That was the mind bender, 0 length, but full dimension 1.
Driven by removing intervals based on pi pit.
Then the Fat Dynamic Prime Cantor Set, FDPCS.
Yeah.
That one was fat, kept a positive length, about 0.6.
Using the gentler 1pk squared removal factor.
Which also meant it had dimension 1, but because it had positive length, and we saw the ghost effect there, excluding primes, increased its size.
With smaller primes leaving bigger ghosts.
And finally, the prime ghost line, PGL. Totally different approach. Remove the countable set of points 1 pan.
Which had 0 measure and 0 dimension itself.
So removing them left the line with full measure 1 and full dimension 1, almost untouched geometrically.
And the thread connecting all of this.
It's this amazing, sometimes really surprising, interplay between the discrete world of prime numbers
And the continuous world of geometry, of shapes and sizes on the number line.
The primes in these different constructions act like sculptors, creating objects with properties that just mess with your intuition about size and dimension.
They really do challenge our basic notions.
It definitely makes you think, doesn't it? What if you used other number sequences, not just primes, Fibonacci numbers, perfect numbers?
What kind of geometric objects would they sculpt?
Yeah. What kind of mathematical ghosts might they leave behind? And maybe this is a bit out there, but could these abstract things,
Born purely from number logic.
could they actually have some weird, unexpected connection back to the physical world? Maybe something we haven't seen yet.
That's the big question, isn't it? Where else might these deep connections between numbers and shapes show up? It's certainly food for thought.
Definitely something to ponder.
Indeed. Exploring these sets really opens up a different way of seeing that fundamental link between arithmetic and geometry. It's much deeper, much more intricate than you might first guess.
That brings us to the end of this particular deep dive. We really hope you found this journey into the prime-sculpted world as, well, fascinating and thought-provoking as we did.
Yeah, it's been fun digging into this.
Absolutely. Until our next deep dive, keep asking questions, keep exploring those connections. You never know what you might find.
Welcome back, everyone, to the deep dive. Last time we went pretty deep, didn't we, into prime numbers.
We certainly did, exploring how they generate those amazing fractal patterns just within a simple line segment.
Yeah, it was wild. We talked about those zero-length fractals that somehow still have dimension 1.
And the fat fractals, too, the ones that seem bigger than they should be.
And those lines haunted by prime ghosts, just points missing for no obvious reason. It was all about how primes, even though they seem random, create this incredible structure.
It really was mind-bending stuff, how apparent disorder leads to this hidden order. And it, sets us up perfectly for today.
It doesn't it? Because today we're asking, can that prime-driven complexity actually affect something really basic, like a circle?
And it leave a mark on geometry itself.
Exactly. So today's deep dive is all about this idea we're calling prime-driven curvature.
Okay.
Basically, we're taking that feeling of prime expansions and contractions from the fractals and seeing what happens if we project that influence onto a smooth shape. The mission is to figure out if primes can actually, bend or warp geometry.
And you've picked a great starting point for this. Very clean.
Hope so. Let's start with maybe the simplest, most elegant shape in 2D, the unit circle.
Right. X squared plus y squared equals 1.
Exactly. X2 plus Y2 is 1. That's our baseline, Perfect Euclidean geometry. Everything nice and flat, predictable distances.
The undisturbed landscape.
Precisely. But now, let's introduce a bit of prime. Mischief.
Okay, mischief, I like it.
Imagine that because of how primes are scattered, how they make those fractals, there's a kind of geometric overflow.
Overflows.
Yeah, the primes are subtly pushing or pulling on our perfect circle. We can show this by just tweaking the equation slightly. X2 plus Y2 equals 1 plus delta.
Ah, the delta.
Yeah, that little delta is the overflow, the extra geometric effect from the primes. Now, delta could be positive somewhere, making the circle bulge out.
Or negative, making it warp inwards.
Exactly. So our perfect circle suddenly has these prime-induced wobbles.
So we're introducing a disturbance, but one shaped by the primes themselves.
And here's where it gets interesting. We don't just leave it as arc2 plus y2 equals 1 plus delta. We try to force it back to the original unit circle's radius.
Okay, how do we do that?
Think of it like a lumpy balloon you're trying to squeeze back into a perfect sphere mold.
Yeah.
You still feel the lumps inside, right?
The internal stress.
So polar coordinates help here.
Yeah.
Distance normally is always 1 for the unit circle.
Right, constant radius.
But now, with the prime influence, the radius becomes r41 plus delta.
Ah, so the radius now depends on the angle, because delta does.
Exactly. Some angles feel more prime push or pull than others.
Got it.
And the next step is like smoothing out that lumpy balloon. We apply a scaling factor, let's call it. It's SWOIT1 plus delta.
Okay, so 1 over the new radius.
Pretty much. Its job is to push or pull that varying radius back to exactly 1. So if delta's positive, a bulge.
You need to shrink it so is less than 1.
Right. And if delta's negative, a dent.
You just stretch it so it's greater than 1.
Exactly. So the result is, visually, we end up back at radius 1 everywhere. But
the amount of stretching or shrinking we had to do is different at every angle.
that's the crucial part. The underlying geometry isn't uniform anymore, even if it looks like a circle on the outside.
We've created a non-standard Euclidean circle. Interesting.
Yeah. Every point has felt a unique pullback, and this non-uniformity, that's our key to curvature.
Because curvature, in normal geometry, measures how much something bends away from being flat. For a standard circle, it's constant.
Yeah, it's just 1 over the radius. So for our unit circle, curvature is just 1 everywhere. Nice and simple.
Predictable roundness.
But our prime influence circle, because of that uneven scaling...
The curvature can't be constant. It must vary with it.
Exactly. And to understand this prime-driven curvature, we need to look closely at how that scaling factor behaves.
Okay.
So first, there's S itself tells us the local compression or expansion. Then we look at how fast it's changing as we move around the circle. That's the first derivative.
The rate of change of the scaling.
Right. But the real measure of the curvature, the bendiness caused by the primes, comes from how that rate of change is itself changing.
Ah, the second derivative.
That's the one. We're interpreting that second derivative as the prime-driven curvature.
So it's not just the scaling, but how rapidly the need for scaling changes around the circle. That reveals the underlying prime structure.
You got it. Think of it as how much the circle has to locally wiggle or kink to cope with those prime expansions we forced back to radius 1.
Like that rubber ring analogy, stuffing an uneven ring into a perfect mold.
Exactly. Where the ring was most inflated or deflated, it would bunch up or stretch out the most to fit.
Yeah, extreme changes.
Those points of intense bunching or stretching where the shape changes most rapidly, that's like our curvature maxima and minima, it's the geometric strain from the primes.
It's a great visual. This tension between the prime overflow and this constraint of the circle.
Yeah. And this begs the question, why primes?
Good question. Couldn't we just use any function and do this math? What makes primes special here?
That is the key question, isn't it? And you're right, mathematically, you could use any delta, but primes bring something unique.
What's the special sauce?
First, their distribution. It's not random, not uniform, but it follows deep patterns, like the prime number theorem gives us their average density.
Okay, their inherent irregularity.
Second, maybe this delta function is directly linked to those prime fractals we saw last time. Maybe it's built from sums involving primes in some way.
So the structure of delta itself reflects prime number theory.
Right. And third, there's often this sense of self-similarity with primes and fractals, like patterns repeating at different scales. Imagine a small prime causing a tiny ripple and a huge prime causing a similar but maybe smaller ripple elsewhere.
So taken together, a prime-based delta wouldn't be smooth or simple.
Exactly. It would likely lead to a scaling factor that's incredibly complex, maybe with infinite little peaks and valleys, like a fractal ring.
Okay.
And then the second derivative of that, our curvature, would itself be incredibly intricate, maybe even fractal-like, a fractal curvature.
Wow. Capturing the deep structure of the primes and the geometry.
And this brings us back to the fractals from last time. Can we connect this overflow, delta theta, to those stereotypes?
The fat fractals, zero length, the ghost sets?
Yeah. Remember, fat fractals suggested abundance, leftover thickness, maybe a positive, an outward bulge is like a geometric sign of that abundance.
And then the zero length ones, suggesting scarcity.
Could correspond to regions where delta theta is negative and inward warp, a geometric deficit.
Okay, that makes sense. What about the ghost sets, the missing points?
Maybe they contribute to the really fine, almost invisible texture within delta.
Yeah.
They don't change the overall size, but they add to the complexity, the tiny fluctuations.
So the specific way primes generate fractals could directly shape this geometric overflow.
Exactly. And you could think of delta theta more formally, perhaps, as like a sum of effects from all the primes.
Like delta varepsilon?
Yeah, something like that, where each varepsilon is the impact of the coth prime at angle. Maybe it's only strong in certain directions related to that prime's patterns.
And adding them all up gives the total bulge or shrink at each angle.
Right. And it's the act of forcing this complex prime-infused shape back to a simple unit circle.
That creates the stress, the geometric memory of those prime expansions.
That's it. This stress, visible in the non-uniform scaling and its derivatives, is the prime-driven curvature.
It's hard not to think of general relativity here.
I was just thinking the same thing. In GR, mass and energy tell space-time how to curve.
Right. Matter curves geometry.
Here, we're proposing an analogy. The prime expansions, the overflow delta, are like the energy momentum.
And the resulting curvature from forcing it back to R1 is like the space-time curvature.
Exactly. Now, it's crucial, like you said before, this is an analogy, a conceptual tool.
Yeah, absolutely. It's not claiming to be physics in the standard sense.
No, but it's a really provocative way to think about how discrete things like primes could influence continuous things like geometry. We could even playfully call it prime gravity.
Yeah, prime gravity. I like it. A model where geometry is driven by number theory, not mass energy.
Just a conceptual model, but fun to think about.
So while it might not be mainstream physics, could this line of thought connect to maybe more advanced abstract math, where number theory and geometry do meet?
That's a great question. And yes, absolutely. There are incredibly deep areas of math exploring these links. You've got things like the Langlands program,
which tries to connect number theory to representation theory and geometry. Incredibly complex stuff.
Right. Or arithmetic geometry, which uses geometric tools to solve number theory problems. Our little prime curvature idea, while super simplified, maybe hints at that same deep interplay between the discrete primes and the continuous shapes that those fields grapple with.
It suggests the patterns of primes might hold secrets about geometric structures.
Exactly. Okay, let's make it slightly more concrete. A simple example.
Please.
Imagine near angle, the primes cause a small outward bulge. Let's say delta 0 is about, I don't know, 0.01.
Okay, a 1% overflow there.
And maybe over at 90 degrees, there's a slight inward dent, so delta 2 is, say, 0.005.
A 0.5% deficit there.
And everywhere else, maybe just tiny random noise in delta from all the other primes.
So definitely not uniform.
Definitely not. Now remember, our formulas, squart1 plus delta, and the scaling eta.
Got it.
At delta 0.01, the radius is roughly 1.001. That's roughly 1.005.
Okay, slightly larger than 1.
So the scaling factor is 1.005, which is about 0.995.
Meaning we had to compress the radius by about 0.5% at that angle to get it back to 1.
Exactly. And it's how this scaling factor changes as we move away from theta 0, especially its second derivative, that tells us the curvature.
Right. How quickly does that 0.5% compression need to adjust?
Precisely. Imagine zooming in really close at delta. The shape wanted to bulge out because of delta, but we forced it back to radius 1. This creates a tiny fold or wrinkle in the geometry right there.
A microlump folding back on itself almost.
Yeah. That little bend, that geometric strain caused by pulling the prime bulge back, that's what the prime-driven curvature is measuring locally.
A subtle ripple reflecting the hidden prime influence.
Exactly. And thinking about this prime geometry, it opens up some really cool possibilities for future thought experiments.
Like what?
Instead of a circle, what about a sphere? Or a hypersphere in more dimensions?
So delta would depend on multiple angles or coordinates.
And the prime curvature would be this complex field over a higher dimensional surface.
Expanding the canvas, yeah.
Or what if we think about delta as changing over time, as we include more and more primes in whatever sum defines it?
The shape would subtly morph, the curvature patterns would flicker and evolve.
Maybe you could get into dynamical systems, how the shape evolves driven by the prime sequence.
A geometric evolution powered by number theory.
That's fascinating.
And if the prime affects the fractal characteristics,
Then maybe the curvature itself would show fractal patterns, self-similarity in the kinks and wrinkles at different scales.
could be a truly fractal curvature. And maybe there's even an analogy to potential energy. Could we view delta theta as some kind of potential field, and minimizing some energy would smooth out the prime bumps? Interesting idea.
Maybe even hints at prime-based waves, who knows?
It certainly opens up a whole landscape of mathematical questions.
It really does. All these ideas just highlight how the discrete world of primes might deeply influence continuous geometry in ways we don't normally think about.
A powerful connection between different mathematical realms.
So yeah, that brings us towards the end of this particular deep dive on overflow, projection, and prime-driven curvature.
We covered a lot of ground.
We did. Started with a simple circle. Imagine this prime overflow, OTA, projected it back to radius 1 using...
Define this new kind of curvature based on the second derivative of that scaling factor, reflecting the prime influence.
And as we've stressed, it's more of a conceptual framework, an analogy.
But a really compelling one for thinking about number theory and geometry together.
Absolutely. And future thoughts in this prime geometry could go anywhere trying to actually calculate from prime fractals, seeing how fractal dimension relates to curvature. It's wide open.
Leaves us with plenty to ponder.
Definitely. And we hope, for everyone listening, this has maybe sparked some curiosity about just how interconnected mathematics can be.
Yeah, the idea that discrete prime patterns and smooth geometric shapes might be fundamentally linked.
It really makes you wonder, doesn't it? If mathematics itself, maybe even the universe, operates on this kind of deep interplay between numbers and shapes.
That's a captivating thought to end on.
It is. So until our next deep dive, keep those minds open, keep looking for patterns, and maybe, just maybe, you'll spot the hidden logic of primes shaping geometry somewhere unexpected. Welcome to the deep dive. Today, we're venturing into some really fascinating territory.
Oh, yeah.
Yeah, the surprising link between prime numbers, the basics of arithmetic and geometry, which is all about shapes in space.
They seem like completely different worlds, don't they? Numbers versus shapes.
Exactly. But we're going to explore how they actually intertwine in some pretty remarkable ways.
It's quite compelling, actually, how these very distinct, indivisible numbers, the primes, can somehow shape geometric structures. It often leads to stuff that feels not very intuitive.
Totally. And we'll touch on some cool examples, like these things called the Dynamic Prime Cantor Set and the Fat Dynamic Prime Cantor Set. They sound complex, and they are fractal-like things built from prime.
We won't get totally lost in those today.
Oh, no, they're good examples. But our main focus is going to be something called the prime ghost line.
Ah, yes. That really hits the core issue.
It does. And the main idea, the sort of paradox we're wrestling with, is this. 2 points can be arithmetically distinct, but geometrically close.
That's the tension right there.
Yeah, this clash between what a number is, its identity, and where it sits in space. That's what we're really diving into.
Okay, so let's start with that first part. Arithmetic identity. What do we mean by that? Like a number's fingerprint.
Yeah, that's a great way to think about it. It's like the number's fundamental DNA within the whole system of numbers, everything that makes it uniquely it.
Okay.
So take the fraction 13, simple enough. Its prime factorization involves just 3. It's 3 to the power of an extra 1.
Right.
Now compare that to, say, 1 over 5 cubed, so 1 over 125.
Okay, different prime. 5 instead of 3. And a different power.
Exactly. Immediately, it's built on a totally different prime foundation, the prime 5, raised to the power of 3 down there in the denominator. So the point is, numbers have this like internal structure beyond just their decimal value.
Precisely. Even though 13 is 0.333.
Yeah.
And 1125 is, what, 0.008? Tiny.
Very small, yeah.
But their underlying arithmetic makeup is worlds apart. Different prime factors, different powers. They behave totally differently in number theory, like in modular arithmetic, for instance.
So they're from different arithmetic families, you could say.
Yeah, exactly. So even if they end up looking close value-wise, their fundamental identity, their arithmetic identity, is completely unrelated. It's about those core properties.
Okay, I think I get that. The unique prime fingerprint. So how does that bump up against this idea of geometric closeness?
Geometric closeness is much more visual, maybe. Think about the plain old number line.
Okay.
If 2 numbers are geometrically close, it just means they're neighbors on the line. They're near each other.
Simple enough.
Now, imagine we start putting points on this line. Let's put one at 12, then another at 13, then 15, 17, 111, using the reciprocals of prime numbers.
Okay, so 12 is 0.5, 13 is about 0.33, 15 is 0.2. Right, they're all clustering down near 0.
Exactly. As that prime in the denominator gets bigger, 13, 17, 19, and so on the fraction itself gets smaller and smaller, and those points on the number line, they just get squeezed tighter and tighter towards 0. If you zoomed out far enough,
You wouldn't be able to tell them apart. They just look like 0.
pretty much, they blur into what seems like a single point visually.
Okay, so arithmetically, like we just said, 117 and 119 are totally different beasts, different prime foundations.
Absolutely distinct.
But geometrically, on the number line, they're just 2 tiny numbers incredibly close to each other and incredibly close to 0.
And that's the heart of the contradiction, isn't it?
Yeah, it feels like it.
Arithmetic insists they're fundamentally different. Geometry, looking at their position, says they're practically the same, especially as they approach 0. And it's this contrast, this tension between identity and location that opens the door to some really cool and weird mathematical ideas.
Which I guess brings us neatly to this prime ghost line, the PGL. It sounds spooky.
Haha. Yeah, it does have a certain ring to it. But it's a fantastic, concrete example of this tension.
So what is it? How's it defined?
Okay, so mathematically, you start with the basic interval on the number line from 0 to 1, including 0 and 1.
Right, the unit interval.
Then you remove a specific set of points. Let's call the set we remove R, and R contains all the numbers that look like 1 over p to the power of k.
Okay, unpack that. P is a prime number.
Yep, p is any prime number 2, 3, 5, 7, and so on. And k is any whole number power starting from 1. So k can be 1, 2, 3, 4.
Got it. So we're removing 12, 13, 15, 17. Those are p to the power of 1.
But also 1 over 2 squared, which is 14, and 1 over 3 squared, which is 19, and 1 over 2 cubed, 18, and 1 over 5 squared, 125.
Okay, so for every prime, you remove 1 over that prime, 1 over its square, 1 over its cube, and so on, forever.
Exactly. You do that for all primes and all positive integer powers.
Wow. Okay, so we're taking that nice solid line segment from 0 to 1, and we're punching out. It sounds like an infinite number of holes, because there are infinite primes and infinite powers for each prime.
You're absolutely right. It is an infinite number of points that get removed. Every single one of those points we remove, like 111 or 17 cubed, has its own unique arithmetic identity based on its prime and power.
Yeah, based on what we discussed earlier.
But here's the kicker. This is the really wild part. The total amount of length you remove by taking out all those infinite points is 0.
Wait, 0? How can that be? You take away infinitely many things, shouldn't the total length shrink, even just a tiny bit? That feels wrong.
It does feel wrong. It's super counterintuitive. This gets into something called measure theory, which is how mathematicians rigorously define the size or length or area of sets, especially infinite ones.
Okay.
The key idea is that a single point on the number line, just one point, has zero length.
Right, a point has no dimension.
And it turns out, even if you take an infinite collection of points, as long as you can count them, even if it takes forever, listen, 12, 13, 14, 15, 18, 19, the total length of all those points added together is still zero.
Like adding 0 plus 0 infinitely many times?
Yeah. So even though we remove infinitely many arithmetically distinct points, they are so spread out, so thin, geometrically speaking, that they're like geometric dust. They don't occupy any actual length on the line.
That's amazing. So the punchline is...
The punchline is that the prime ghost line, the thing that's left after you remove all this infinite dust, still has a total length or measure of 1.
the same length as the original interval, even with infinite holes punched in it.
Exactly the same length. It's a full measure. It's like the line is still complete in terms of length, even with all these ghostly gaps where the prime power reciprocals used to be.
Wow. Okay. That really does show how geometry can be almost blind to these individual arithmetic identities.
It really does. The PGL perfectly shows how numbers with very strong, unique arithmetic fingerprints can have basically zero impact on the geometric size of the space they're in.
So geometry cares more about the continuous flow, the proximity, the overall size, and these individual isolated points just don't register on that scale.
That's a good way to put it. It highlights that philosophical split we talked about. Geometry's focused on distance, closeness. Arithmetic is focused on structure, uniqueness, the inherent properties.
Let's go back to 117 and 119 for a sec.
Sure.
Geometrically, they're practically sitting on top of each other near zero. You'd need a serious microscope.
Absolutely, very close.
But arithmetically, because 17 and 19 are different primes, their worlds are totally separate.
Completely. Think about it. Their reciprocals have different prime factors, obviously. They behave differently in modular arithmetic. What remainder do you get when you divide by 17 versus 19? Totally different patterns. Things like Euler's totient function give different values. They just act differently in equations.
So in arithmetic, that tiny difference between 17 and 19 is huge. It changes everything.
It's fundamental. But geometry just sees 2 points that are very close. It smooths over those fine distinctions.
It's like arithmetic sees these incredibly detailed, unique individuals, and geometry sees a crowded room where everyone's blurred together.
That's a nice analogy. And when mathematicians try to bridge that gap, maybe with ideas like prime curvature or similar concepts, you get this geometric tension. It comes from trying to reconcile the arithmetic focus on identity with the geometric focus on proximity. They just value different things.
This whole idea, it feels like it could resonate beyond just numbers, couldn't it? This tension between being distinct and being close.
Oh, I think so. It's definitely tempting to draw parallels, isn't it? You start wondering where else this kind of duality might show up.
Like where?
Maybe, and this is just speculative, think about quantum physics. You have identical particles like electrons. Maybe they follow different paths, have unique histories in a way. But under certain measurements, they become fundamentally indistinguishable. Their observable properties, their geometric state in some abstract space, might be identical despite their different arithmetic path histories. Does that make sense?
Yeah, that's really interesting. Like, their individual story gets lost in their current shared state. What about something completely different, like language?
Oh, definitely. Think about, say, AI and natural language processing.
Yeah.
You have words, right? Each word has a distinct meaning, its own semantic identity.
Like its arithmetic profile.
Exactly. But in these huge language models, words are often represented as points in a high-dimensional space, like a vector. And sometimes words with quite different meanings might end up being very close together in that space, geometrically close, just because they tend to appear in similar contexts in the text data they were trained on.
So semantically distinct, but statistically similar in terms of where they hang out.
Precisely. Their meaning DNA is different, but their location in the semantic landscape is close. It's another version of that same tension.
Huh. And maybe even like on a human level.
How?
Think about people. We all live close together, right? In cities, communities, geometrically close in space and time.
Sure.
But each person has their own unique arithmetic, their history, their experiences, their personality, their thoughts, utterly distinct.
Absolutely. Deeply individual identities.
But then, what happens when you zoom out? Look at society as a whole or global trends. Do those individual distinctions sometimes fade into broader patterns? Does the geometry of the crowd sometimes overshadow the arithmetic of the individual? It makes you wonder about scale.
It really does. At what point does proximity start to blur identity, or vice versa? It's a deep question.
So maybe the big takeaway here is, next time someone just waves their hand at fractions like 17 or 113 and says, they're just small numbers close to zero.
Remember the hidden depths. Remember that beneath that geometric closeness lies a profound arithmetic distinctness. Completely different structures.
Yeah, this tension, this paradox between what a number is fundamentally, its arithmetic soul, and where it sits geometrically, it's actually really beautiful when you think about it.
It is. That tension is really what fuels the weirdness of the DPCS.
It seems to be at the heart of it, this clash between the geometric notion of closeness and the arithmetic notion of identity based on primes.
Leading to this spooky set no length full dimension.
Yeah, spooky is a good word for it, because if you were to zoom in on any tiny piece of the DPCS, you wouldn't find just empty space.
You'd find more structure.
You'd find more gaps, more remaining fragments whose positions were determined by even larger prime numbers further down the sequence. It has this fractal quality, built layer by layer by the primes.
The Post also threw out that term prime gravity. More metaphorical, obviously, but...
Yeah, definitely speculative. But it's this idea that maybe the way primes are distributed isn't just an arithmetic curiosity. Maybe it exerts some kind of...
like a subtle organizing principle?
Perhaps. It's an intriguing thought. Are there deeper connections between number theory and geometry than we usually assume?
It definitely pushes you to think.
It makes you wonder if the DPCS is just this, weird object mathematicians found, a curiosity.
Or if it's pointing towards something more fundamental about how primes shape mathematical reality.
Exactly.
Their specific distribution is the magic ingredient, isn't it? Sparse enough to kill length.
But irregular and persistent enough to maintain that full dimension, one footprint. An infinitely shattered line, almost.
So, wrapping up this deep dive. So think about it. If a set can have literally zero length, take up no space in that sense, but still have the dimension of a line, still be just as complex dimensionally, it forces you to rethink what big and small even mean.
It really does.
And like the blog post wrapped it up so well, if that doesn't make you question how we define big or small, nothing will.
A perfect closing thought. Maybe those prime identities embedded in the set structure really are never forgotten no matter how fragmented it gets.
Makes you wonder.